Okay, so starting off with question number 1. So we have created the structure using 5 rectangles. As you can see, from rectangle 1 to all the way to rectangle 5, we have used these rectangles to create the structure. Upon clicking on mesh number 1, as you can see, I have generated a physics controlled mesh to analyze the structural deformation of the structure. After applying the required loads, we can see the resulting displacement as shown on the color bar here on the right. The maximum deflection at the ends of the horizontal beam is approximately 2.5 micrometers. After switching over to the von Mises stress plot, we can clearly observe a stress concentration right at these inner anchor corners peaking at roughly 160 megapascals. Okay, so in question number 2, we have a beam of 10 micrometers and we are going to set the coordinate system to global coordinate system and apply the force of -3 micronewtons on the free end. And after we compute the study, we can see on the color bar that the maximum tip deflection is approximately 1 micrometer. Okay, for now cantilever B, we are going to change the depth of the beam to 1000 micrometers and we are also going to change the force to -3e4 newtons to maintain the exact same load per unit width. And now upon computing the study, we can see Upon computing this result, the maximum deflection drops slightly. This demonstrates that the massive width restricts lateral deformation, known as Poisson effect, which creates a plane strain condition and artificially increases the beam stiffness. Okay, so now we are going to evaluate crystal direction by applying a 45-degree rotated coordinate system to the silicon material properties. We have set this degree to 45 degrees and now we are going to change the coordinate system to rotated system. And now upon computing the study, we can see an even lower deflection because silicon is anisotropic. Its Poisson ratio is higher in the 100 direction, which makes the stiffening effect from the wide plane strain condition even more pronounced. And now we are going to see these results for the narrow beam. We have changed the depth to 10 micrometers again and have changed the force back to -36 newtons. And now upon computing the study, we can see so now the maximum deflection for the narrow beam is approximately 0.8 micrometers, which confirm it is still more flexible than its wider counterpart.